Hi and welcome to this Leaving Cert Higher Level Sequences and Series video. In this video, we're going to be looking at geometric or exponential sequences and series that appear on the Leaving Cert Higher Level course. So identifying an exponential sequence. So a sequence of numbers that follow a pattern of multiplying a fixed number from one term to the next are called exponential sequences. So remember, for our linear or arithmetic, we were adding the same thing each time. For quadratic, we were adding a number, but there was a pattern to how that number changed. Now we're talking about a multiplication. So for example, 2, 4, 8, 16, 32. What's happening here is we're going to multiply each term by 2. So we multiply by 2, and so on. To work out the nth term, it will look something like this, 2 to the power of n, and that's where we get this idea of exponential, so our exponent or our power. So that n, that number of term, is in the power. Now, we'll look a bit more about where that comes from, but for now, know that we can identify an exponential sequence by understanding what we multiply each term by to get to the next, or by seeing this general term and having it like 2 to a power or 3 to a power, something to a power of n. So let's look at an example here. It asks us what kind of sequence, linear, quadratic, or exponential, or none of these, is given below. So this is revision of a question you would have had at Junior Cert. The language is what gives that away, because we no longer say linear when we're looking at our Leaving Cert sequences, we say arithmetic. Quadratic remains the same, and we'll have a new word for exponential. So we're going to say first check is, so here's our little check system. Check to see is it linear. So check our adding. So I add 2, then I add 6. Okay, so no, straight away it is definitely not linear. But maybe it's quadratic. So then you look and you say, right, if I take my differences, so I'm going to do plus 2, then I have plus 6. Then I've plus 18 and so on. Does that have a common second difference? So plus 4 plus 12? No. Okay, so it is not linear. It is not quadratic. So then our check is, could it be exponential? Could I be multiplying each term to get to the next? So here I multiply by 3. Here I multiply by 3. Here, multiply by 3, and yes, we do have this idea of multiplying, so this is an exponential sequence. So we want to check, first of all, is it linear, as it arithmetic, is it then quadratic, and finally we'll check if it is exponential. So for our questions, as we do Leaving Cert higher level questions, what you're going to understand and what you're going to see is they'll generally tell us the type of sequence and using that fact, because there's a lot more maths we can do that way. So let's talk about geometric. So a geometric sequence is just the new term we have for an exponential sequence. The reason we use the term geometric is because it's given here in our log tables. So just like it's fine to call it exponential, but just to be aware when you go to find any of your formulae, they're going to be under geometric sequence in your log table. So just like with our exponentials, same thing, we're going to be multiplying a term by a constant. So the geometric sequence looks like this. It starts with A, and if you've already gone back over your sequences, you'll know that A stands for our first term. Then you multiply A by some number, we're going to call that OR, and then when you get A OR, you multiply that by OR, so you get A OR squared, and so on. And we start to see these powers, these indices, these exponents appear. So A is that first term, and OR is a new letter for us. When we had arithmetic sequences, we had this idea of a common difference, which was D for difference. Here, it's the factor between the terms. OR is called the common ratio. So ratio is about division. So when you divide one term by the previous term, we're getting basically what number do you multiply one term by to get to the next. So our common ratio. So in every geometric sequence, term 1 is A. Okay, so that is the same as we've had before. To get the common ratio, you divide T2 by T1 or any term divided by its previous term. And that's what it's given us here. It's saying Tn plus 1. So this term divided by its previous term. So our general term here, that Tn is equal to A times or to the power of n minus 1, that's actually given in our log tables. So here's our log tables. We've already seen our arithmetic. So we're down on this bottom piece in geometric. And here is that general term Tn. The A is common. It's the same thing no matter what type of sequence we're looking at. But we now have an OR, which is the common ratio. So let's explore these geometric sequences a little bit more. So it says find Tn and then T10 of the geometric sequence. So I have my formula pulled out here. So what I need to have is A and OR. So they're the two pieces of information I have. The sequence is 1 and then a quarter and then a 16th and then 1 over 64. So we need to figure out what am I multiplying, because it told us it was geometric. What am I multiplying each term to get to the next? So I'm going to multiply by a quarter. Okay, so now I have A, which is 1, and my OR, which is a quarter. So to get Tn, it's going to be A, which is 1, times a quarter to the power of n minus 1. Now, we're going to do a little bit of cleanup here because 1 multiplied by anything doesn't change it. So this is the same as a quarter to the power of n minus 1. Now you can clean it up further if you want. We know that 1 to any power is just going to be 1. To apply a power to a fraction, you apply it to the top or the bottom, the top and the bottom, apologies. So you'd have something like 4 to the power of n minus 1. You can play around with your indices there if you want, and you get something like 4 over 4 to the power of n. However, this is absolutely perfect. That's all they're looking for. So now the second piece they want is T10. So T10 is going to be a quarter to the power of 10 minus 1, which is a quarter to the power of 9. And that gives us 1 over 262,144. So example 3, let's do a bit more working with the geometric sequence. Here is a geometric sequence that gives us T3 and T6. So we're trying to find A and OR and then write down the first 6 terms. What I like to do in cases like this is really to illustrate what we've been given. So I'm going to draw out space for the 6 terms. This is 32 and this is 4. So this is T1, T2, T3, T4, T5, T6, and we know that it is geometric. So basically I'm multiplying it by some number, common ratio, which is OR. Now when I get to here, I can do a little bit more because I'm multiplying 32 by OR. So that's going to give me 32 OR, and then I multiply by this again and I get 32 OR squared. And if I do it another time, T6 should actually be 32 OR to the power of 3. So I know that I can say, well, if I take 32 and I multiply by OR to the power of 3, that equals 4. Now I'm trying to solve for OR. I'm going to divide both sides by 32. And that gives me OR to the power of 3 is equal to 1/8. To get OR, I'm going to do the cubed root of 1/8. So that gives me OR is equal to 1/2. Okay, so now I know that actually this was multiplied by 1/2, multiplied by 1/2, multiplied by 1/2, and so on. Okay, so that helps us somewhat, but they've also asked me for A, the first term. So I'm going to work backwards here. So what number multiplied by 1/2 gives me 32? So if I have a number and get 32, the number must have been 64. And going the other way, again, I'm doubling it, it's 128. So now I need to write out the 6 terms of the sequence. So I have the first 3 and I have term 6. So now I just need to write out term 4 and term 5. So we have 128, 64, 32. The next will be halved, so it'll be 16, then 8, and then 4. So it's using similar logic that we had when we were looking at arithmetic sequences. However, in this case, we're dividing and multiplying rather than adding and subtracting. Example 4. So this is a great example, and we've seen something quite similar to this appear on our paper. So we have 3 terms here, and we're told that they're the first 3 terms of a geometric sequence. So 3, x, and x plus 6. And it says find the value of x and the 10th term of the sequence. So what we know is if this is geometric, that when we multiply, if we multiply 3 by or, we get x, and if we multiply x by x plus 3, x by or, we also get x plus 6. So we can set this up and do like a simultaneous equation if you want. However, a much easier method to work is this. If this is term 1, term 2, and term 3, taking term 2 and dividing it by term 1 should give us the same answer as taking term 3 and dividing it by term 2. Because remember, we're talking about a common ratio division. So we know that x divided by 3 should give me the same answer as x plus 6 divided by x. Now I have an equation in terms of x, and I just need to get rid of my fractions. So I'm going to multiply both sides by 3x to get rid of my fraction. So x cancels here, 3 cancels here. X by x is x squared equals 3x plus 18. So now I have a little quadratic. X squared minus 3x minus 18 equals 0. And now we're going to go and solve for x. I'm going to use factorization. You can use guide number here. That's absolutely fine. And this will end up being minus 6 plus 3, which ends up giving us x equals 6 or x equals minus 3. Now watch the question. It said the value of x. So one of them is incorrect. So this one here is incorrect because they told us that they were positive terms. So here is my value of x. Now they want us to find the 10th term of the sequence. So in order to find the 10th term of the sequence, we're going to have to build the sequence up. So the sequence is 3, then x, which is 6, then x plus 6, which is 6 plus 6, which is 12. So that's my sequence. I know that I am each time multiplying by 2. I want the 10th term. Now, it's up to you. You can keep going with this. So we'd have 24, 48, 96, 192, 384, 2 more, 768, and 1536. Now, I'm not a huge fan of that method. I would prefer to make our general term. So we have Tn is a or to the power of n minus 1. Our first term was 3. Our common ratio was 2. So that gives me Tn is 3 times 2 to the power of n minus 1. Then I have T10, 10th term. 3 times 2 to the power of 10 minus 1, which is 3 times 2 to the power of 9. And that can go into your calculator and we'll get 1536. Now, just some things that can go wrong and do go wrong is, and I'm going to do it in purple, so this is wrong. Here, sometimes students clean that up 6 to the power of n minus 1. And that is not correct because you need to follow BIMDAS. And I know that's quite a basic thing, or BOMDAS, or whatever you did in primary school. But we're basically saying you must deal with the indice part before you do the multiplication. So it is incorrect to multiply 3 by 2 and then apply the indice. So be so careful with this. Either method is perfect. I would prefer using the TN method. If this came up in an exam, they might ask you one that's so far into the sequence that you'll have to use your general terms. So it's good to be able to work with it. But both methods here would be absolutely fine. Example 5. So the product, so that means multiplication, the product of the first three terms of a geometric sequence is 216, and their sum, so when you add them together, is 21. Given that the common ratio or is less than 1, find the first three terms of this sequence. Okay, so what we're going to do is we're going to set up the sequence. We don't know anything about the sequence itself, so we're going to start with the first term as A. The second term will then be A multiplied by OR, so that's A OR. And then the next term will be A OR squared. So we're getting this sequence in terms of A and OR. So now what we know is if you add A plus A OR plus A OR squared, that you should get 21. And if you multiply A by A OR by A OR squared, you should get 216. Now, this product piece, so I'll just label it, this is the sum piece, and this is the product. So the product piece is a little bit easier to work with at the moment. We have A to the power of 3 or to the power of 3 is equal to 216. So A or is going to be equal to the cubed root of 216. So that gives me A times OR is equal to 6. So that's kind of our first equation. It's going to be a simultaneous equation, really. And then we can work over here with our sum. So we have A plus A OR plus A OR squared equals 21. So what I'm going to do is use the fact that we have this first equation, A OR equals 6. And I'm going to work with, it doesn't really matter. You can work with A, you can work with OR. I'm going to do A. So A is equal to 6 divided by OR. So I'm isolating my A so I can substitute it in here. Now, you could absolutely do it with OR. That's absolutely fine. No issue at all. So 6 over OR times OR plus 6 over OR times OR squared, and that equals 21. So they cancel, leaving OR, they cancel, and we've a cleaned up version of 6 over OR plus 6 OR, and that equals 21. Now we can do a little bit of cleanup, or you can get rid of the fractions, it doesn't matter. So I'm going to multiply across by OR to get rid of my fractions. So that leaves me 6 plus 6 OR plus 6 OR squared equals 21 OR. So what we actually get is a quadratic, which is 6 OR squared. Bring that 21 across, and that gives me minus 15 OR plus 6 equals 0. So just cleaning it to get a bit of space, 6 OR squared minus 15 OR plus 6 equals 0. Let's use guide number here. Guide number is plus 36. So that's going to be minus 3 minus 12. That'll give us our minus 15. You can use minus b formula here either. 6 OR squared minus 3 OR minus 12 OR plus 6 equals 0. 3 OR here is common, leaving us with 2 OR minus 1. Minus 6 is common here, leaving us with the 2 OR minus 1. So brackets are the same. So we get 3 OR minus 6 times 2 OR minus 1 equals 0. So OR here is going to be 6 over 3. So OR is equal to 2. Here OR is equal to a half. Now, they told us that the common ratio was less than 1, so this one is not correct. This is our common ratio. So going back to equation 1, we had that A was equal to 6 divided by R. So therefore A is equal to 6 divided by a half, which is the same as 6 by 2, which is 12. So now we can set up our sequence. So we start at 12, our next term is half, so that's 6, and our next term is half, so that is 3. So very much working with all of our algebra techniques in these questions. So when we see geometric come up, it's a nice question to involve a lot of other techniques from other areas in the course. Example 6. So this is our last geometric sequence question, and it asks us to find the number of terms in this geometric sequence. So sometimes I find in the questions they haven't them spaced out very well, and I need space really for my head to be able to process the sequence. So I like to write it out with a bit of space. So I want to understand this is a geometric sequence, so what is my common ratio? So I'm basically multiplying by a third. So anytime you see a sequence, a geometric sequence that is decreasing, so getting smaller, our common ratio will be a fraction. So it's kind of like we're dividing instead of multiplying, but we're always multiplying. We're just going to multiply by a fraction instead, because a fraction has that inbuilt division. So we figured out A is equal to 81, and we figured out that R is equal to a third. So I'm going to come up with my general term, Tn, nth term, and that is A, which is 81, and R, which is a third to the power of n minus 1. Now remember, you cannot multiply BIMDAS. You must leave this as is. You cannot multiply 81 by a third. You must do the indice piece first. I now want to figure out which term this is. So I'm going to let my Tn equal to 1 over 27 and figure, don't know what went wrong there. That should be n minus 1. And figure out what value is n when these two are equal. So the first thing we're trying to do is we're trying to isolate that n. So I'm going to divide both sides by 81. Okay, so I have 1 over 27 and I'm going to divide that by 81. So we end up with 1/3 to the power of n minus 1 is equal to 1 over 2187. Now, I'm going to use my laws of indices here, so if you need that open, it's in your log tables. But I can apply this power to the top of the fraction and the bottom of the fraction. But 1 to the power of anything will still be 1, because it doesn't matter how many times you multiply it by. So this becomes 1 over 3 to the power of n minus 1, and that equals 1 over 2187. Now, what I like to do when I'm dealing with fractions, and I'm going to have to move over here, is if two fractions are equal, their reciprocals are also equal. So reciprocal is where you flip the fraction. So that is 3 to the power of n minus 1 should also be equal to 2187 because they're both over 1. You have a few different options here that you can use. You can go straight to logs. I'm going to use my indices once more. And I'm going to separate this into 3 to the power of n and 3 to the power of minus 1. It's good to kind of work with our rules of indices here. And that is 3 to the power of n divided by 3, 2187. So we're going to multiply both sides by 3. Okay. And when I multiply both sides by 3, I get 3 to the power of n equals 6561. And now you can either use trial and error or logs. So it's log to base 3 of 6561, that equals n. And that gives us n equals 8. Now you could have applied the log at this step here and got the same answer, but it's good to get a bit of practice in with our rules of indices. So that n, that term, should always be a positive whole number, which it is. So the number of terms, therefore there are 8 terms, because that final term is term 8, so therefore there are 8 terms. So now that we've looked at the geometric sequences, we're going to move into geometric series. So remember that a sequence is a set of numbers, and the series is then when those numbers are added together. So our formula here is Sn, which stands for the sum of the first n terms. That's up here at the top. And we have a bracket 1 minus or to the power of n all over 1 minus or, where a is our first term and or is the common ratio. Remember that common ratio, what do I multiply each term by to get to the next? So this is called the finite sum of a geometric series, and because there is something called an infinite sum. So we're going to look at both of those. So we have here, find T5 and S5 of each of the following. So they haven't told us they're geometric, so we just want to double check that is the case. So yeah, I'm multiplying by 3 and by 3. So the first two, well, the two things I want to pull out is A, my first term, and my common ratio, or. I then am going to get Tn. I'm going to do it using the general term, so Tn. So that is A or to the power of n minus 1. I'm then going to use that formula to get T5. So that is just 3 to the power of 5 minus 1, which is basically 3 to the power of 4, and that is 81. Then it wants us to find the sum of the first 5 terms, so S5. Again, I'm going to use my formula. The formula is A 1 minus or to the power of, sorry, I'm actually going to do Sn and then I'll do S5. So Sn first. So 3 to the power of n all over 1 minus 3. Now that can be cleaned up as 1 minus 3 to the power of n. It's multiplied by 1, which doesn't matter, all over minus 2. So then coming along to do S5, we get 1 minus 3 to the power of 5 divided by minus 2. And that gives us 121. Now you could have continued on. We had 3 terms here. So the next term is 27. The next term is 81. So there's my 81. And actually quite quickly you can add 1 and 3 and 9 and 27 and 81 and still get your 121. But I really wanted to practice using those formula. So our second series we have here, just double checking that it is a geometric series because they didn't say that, and yes it is. It is a geometric series where a is 1 and or is a quarter. So Tn is going to be 1 times a quarter to the power of n minus 1. So T5 is going to be just, the 1 doesn't matter, so a quarter to the power of 5 minus 1, which is 4. And that gives us 1 over 256. I'm going to do Sn then, that's 1 bracket 1 minus a quarter to the power of n. I will use my brackets here just to make sure that everything is entered correctly when we get to the calculator. I'm going to do S5 here, so that's 1 minus a quarter to the power of 5 all over 1 minus a quarter. And that gives us an answer of 341 over 256. I like to leave things as top heavies. If you come along to the sequence just like before, you could have wrote this as 1 over 64 and this is 1 over 256, and then you could have added those together. So you can add 1 and a quarter and then a 16th and then 1 over 64 and then 1 over 256, and when you do that you get the same answer. So example 8, again another finite sum of a geometric series. So in a geometric series we have T3 is 32 and T6 is 4. It asks us to find A and or, and hence find the sum of the first 8 terms, S8. So we've done something like this, something similar before. So we're going to draw it out. T1, T2, T3 we know, T4, T5 and T6, and that is 4. Remember, this is geometric, so each time I move from term to term, so we call that our term to term rule. Our term-to-term rule is multiply by or. And what we can say is this is 32 or, this is 32 or squared, and this is 32 or cubed. So what we get is 32 or cubed is actually 4. Dividing both sides by 32, we get an eighth. Or is then the cubed root of an eighth. So that gives us or is equal to a half. So that's great because now I know that this is actually a half. I can start filling in the previous terms. So my previous terms then, what number multiplied by a half gives me 32? Must have been 64, and then 128. So what I've now discovered is my first term A is 128. My common ratio or is a half, and I want to get Sn in the first instance, so the sum of the first n terms. So that's 128. 1 minus a half to the power of n, again use your brackets to help, all over 1 minus a half. They wanted us to find S8, so that is 128 times 1 minus a half to the power of 8, all over 1 minus a half. That can go straight into your calculator, and we get 255. So now we're going to look at the last piece that we have about geometric series, and that is this sum to infinity, so the infinite sum. So if I keep adding that sequence, what answer will it go towards? So this is very much linked to the idea of limits. When we have S infinity, so the sum of the infinite terms, this will only work if or, have I got it coming up here? If or is less than 1. So, well, the absolute value of or will be less than 1. So what that means is the sequence has to be getting smaller. If the numbers are getting bigger and you're adding them together, they're going to get bigger, bigger, bigger until they hit infinity. So adding them together will be infinity, and then that answer doesn't make a huge amount of sense. However, if we have a sequence that is getting smaller, it's going to get very, very, very close to 0, but will never actually get to 0. And we can then get an actual numeric value for the sum to infinity. So I just want to make this connection up here. So this is our sum of the first n terms. And when we go to S infinity, effectively what we're saying is n, that number, is getting bigger, bigger, bigger until it gets to infinity. Well, it'll never get to infinity. It's tending towards infinity. Remember, infinity is not a number, it's a concept. So anytime you pick the biggest number you can think of, you can then add 1 or double it and so on. So like there is no point as such, it's just the idea that it's going on forever. So really, if we take a look at the formula here and we say, well, what happens to this formula as the number n gets bigger, bigger, bigger? Well, taking that or is a fraction, as the fraction to a power, and that power gets bigger, 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 this is going to get smaller, smaller, smaller. And it's going to get so small that it's going to effectively get towards, although it will never get to, but it'll move towards 0. So if that goes to 0, 1 minus 0 is just 1. So it's a times 1, which is where our formula comes from. So that idea, if I have like a quarter to the power of n, as n gets bigger, then this thing, that will go to 0. So we would have seen that as a limit as n goes to infinity of, I'm going to use a quarter as an example, to the power of n, that will give me 0. So this is our link here to limits. So the sum to infinity of a geometric series. So find the sum to infinity of this geometric series. So we start these like any of the other questions we have. And we know it's geometric, but we need to find the common ratio. So what do you multiply 16 by to get to 12? So what we do is 12 divided by 16, which is 16 over 12, or 12 over 16, but that simplifies to 3/4. So now you have your first term, which is 16, and your common ratio, which is 3/4, and we're going to sum to infinity. So the sum to infinity is a all over 1 minus or, and that is 16 all over 1 minus 3/4. And you can see here now why if this piece, the or, was bigger than 1, we get a negative down there, so it wouldn't make sense. So here we have 16 divided by 1 minus 3/4, which is a quarter. Dividing by a fraction instead, we can multiply by the reciprocal, and that gives us 64. So if that kept going forever and ever and ever, all the numbers would add to 64. So the final example is one that's a little bit different, and we have seen this asked on the paper. So this is using the sum to infinity of a geometric series to write a recurring decimal as a fraction. So recurring decimals, we see them often on our computer where it pops up with these dots above the numbers. So they want us to write this recurring decimal as a fraction. Now, there are some other ways of doing it. However, when we've seen this up on sample papers, we've seen it asked as using the sum to infinity of a geometric series. So they've been very clear that they want this method. There's no or otherwise. So there is no shortcut here. So the recurring decimal 0, 2 dot, 3 dot is 0.23232323, and this goes on forever. So we can see that each 2, 3 piece is recurring. So what we end up doing here is saying, well, look, this piece could be written as 23 over 100. So really going back to your primary school decimals. And this piece could be written as 23 over 10,000. And this piece could be written as 23 over 1,000,000, 6 zeros. And if you added all these pieces together, and this goes on forever, you would be back to the idea of 0.23 recurring. So what we have here is actually a geometric series. So here, what am I multiplying each term by to get to the next? It's making it smaller, multiplying by 1 over 100. So I have a series where A is equal to 23 over 100 and or is 1 over 100. And we're going to use S infinity to help us. So we have A all over 1 minus or, and when you do that and put that into your calculator, you'll have your answer, and it works out as 23 over 99. Now, just to be aware of other variations of this question, if there was a number here, that number, say that was 2, right? So there's a 2 here. So you'd need to put a 2 in front. It doesn't change this piece. However, my final answer would have to have a 2 put in front of it, if that makes sense. Get rid of all that. Also, just to be aware, if you see something like 0.705 and the dots are like this, that means 0.705, 705, 705. So the dots show the start and the end of the piece that recurs. Okay, we're very used to 1 dot or 2 dots like this, but maybe not the dots that are separated. Also, if you had something like this, what that means is it's 0.233333. In that case, this piece would not be part of the sequence, and we would have to look at all the individual 3's. So this would be 3 over 100, 3 over 1,000, and so on, dot, dot, dot. That would be our S infinity, and we'd also then have to add 0.2 on at the end. So they're all like different variations of it.